Uh, Thank you. I'd like to thank the organizers for inviting me and letting me talk about the results in this uh, of this work on quantum steering. So here I think this talk will be very light in a sense because this is this is not actually about convex optimization itself, the theory, but an application of convex optimization of semi-definite programming, and it's pretty standard. So uh, this is the disclaimer I I have to put here before I begin the presentation. So what we have done in this work, we quantized the instrumental causal networks, and so I begin by introducing these instrumental networks, the classical original version of it. So it's essentially this model for correlated variables, for this pair of correlated variables here, where you can control one of them, one that you presumes that it's the cause of the other one. So we have this variable, which is a control parameter, which we call the instrument, and this allows us to make some, so it's like this minimal, this some sort of a smallest network that you can use to have this uh, causal inference on a pair of correlated variables, right? So with this instrument, we can infer how much of the correlation comes from a direct causal influence, represented by 0 here, and how much comes from a common cause, so which is here represented by this lambda. It's also called the hidden variable if we consider this from the point of view of non-locality and so on. So this network is very relevant for causal inference. It's used in many areas, so econometrics, medicine, and so on. And it's interesting to see what we get by quantizing it, by getting semi-quantum versions or quantum versions of this network, because we know that using quantum correlations, we can get more power to describe what type of correlations we can get from here. So here, for instance, we have this network representing local hidden variables model for Bell non-locality. The probability distribution is essentially described in that way. So we have the common cause actually being the one responsible for the correlation between the variables. And we know that from the Bell's theorem, of course, that this is not the most general model to describe probabilities that happen in nature. So, but if we allow this common cause to be quantum, to be a quantum state that correlates both variables, then we get this a more general probability distribution that has indeed more descriptive power than this first one. So with this, what we did is here we introduced, so as a first step, we introduced this semi-quantum version of the instrumental causal network by quantizing the one of the correlated variables, so the one that we assume to receive the influence, the direct influence. And we call this model the one-sided quantum instrumental model. So here, the object that this network here represents is essentially this assemblage. So which is the common the object from quantum steering, right? So here we have this object, which is the subnormalized state, from which the correlation that appears is essentially a distribution coming from this random variable here that influences both this quantum state and this variable here, which is in a sense, if we see this as the black box from Alice, from one of the parties, this is also what influences the outcome, but also we allow this communication of outcome. So here, if we compare with the usual problem in quantum steering, we see that this instrumental network is essentially the local hidden states model, but allowing for the communication here in this part. So here is, we have uh, this model for the local hidden states, where the biggest difference is that the local state for Bob here, for the quantum site, doesn't have the dependence on A. So putting side by side, we see this more clear. So um, in a sense, this instrumental network is essentially the networks that we see in quantum theory, but allowing this communication of the outcome from the black box. And another step that we have taken was to quantize also the common cause, the quantum, the possible source of hidden variable and the correlation between the variables. And here we also have a representative, a direct representative in the quantum theory that we are generalizing here. So if we put side by side, we see that this quantum instrumental model which we obtain is essentially the quantum, the model of quantum assemblages, but with enhanced with classical communication, right? So the quantum assemblages are the ones that are obtained from a shared quantum state with measurements on Alice's side, here represented in this way, sorry. And the quantum instrumental models are the same thing, but now allowing for Bob to apply some map, some generic CPTP map, depending on Alice's outcome. So here is what this introduces. And if we compare, and of course this model here is inherently signaling, so it's intrinsically has this signaling, but and in quantum mechanics you have these no signaling properties in the way that if you average over all possible states that Bob has, if he has no information on Alice's results, then he has this very well-defined local state for him. And we know that this no signaling is, for the bipartite cases, coincides with the set of quantum assemblies, right? So here, if we compare all the models, in a way, we get some pretty obvious relationship between among them. And for instance, if we compare the quantum instrumental, so the ones that I've already talked about, the quantum instrumental and the quantum models are essentially related. So this model contains this one because it's essentially the quantum model increased by communication. The semi-quantum instrumental is the local hidden state increased by the communication. So one model can describe all assemblages from the other. And from the quantum to local hidden state, and from the quantum instrumental to the semi-quantum instrumental, it also is trivial to explain why one can describe the other just by trivializing the type of correlation that you may have between the variables. What's not clear from this, from the diagrams, is this type of correlation, this type of relation here. So if we, by just increasing the power of the model with classical communication of the outcome, but using still classical correlation, if this is already enough to describe the types of correlations that emerge from having quantum states as the source of correlation. And this is what we answered in this work here. And so the way to answer this is that essentially the model described by that semi-quantum instrumental network allows us to formulate an SDP test for it. So if we use the standard techniques that we have in the quantum steering to define local hidden states and so on, we can here describe very well the membership problem for these for the assemblages as a very similar SDP. The only thing that makes the difference is essentially this point here. So of course, we allow our local states that we are looking for to try to decompose our assemblages. We allow them to have this outcome dependence, and then we have to restrict these subnormalized local states here, these subnormalized hidden states here, to have the trace depending only on on lambda, because they are when you see the local state, the local state is which is the ones that depend on the outcome from Alice, and these are normalized. The subnormalization comes from the fact that you have a distribution for the hidden variable for the lambda. So here is what you have. So this trace is equal to this probability depending on lambda for all values of the outcome here. So this membership already tests if your state belongs to if your assemblage already belongs to the semi-quantum instrumental model or not, but it's not strictly feasible. So we can circumvent this by adding some a parameter here to optimize and see if we can get. But another way to make this strictly feasible is to formulate this test in this robustness language. So here we have also this test where you can essentially see the test for membership of the semi-quantum instrumental assemblage by just adding noise here, particularly noise that belong to also to the semi-quantum instrumental model, and see if how much of this noise we need to add until it becomes semi-quantum instrumental. So this test here is in the primal form. The dual form allows us to obtain, of course, a witness, and it's very similar to the test for robustness for steering, but with this this subtlety here that you that this equation here is that this inequality here, sorry, is the same inequality you get in the test for steering, but is broken down in two steps here. So this in quantum steering, you would have this already summed to in A, and you would get essentially the same thing. But this provides us with the test for actually semi-quantum instrumentality. And one of the good things of having this test formulating this notion of robustness is that this can be easily proven to be a resource monotone for any set of free operations that you can imagine. Of course, linear and essentially you just ask of it the property that it preserves the semi-quantum instrumental set, and this shows us that if we are to treat this non-instrumentality, this property of not being semi-quantum instrumental as a resource, then this robustness already measure how much of this resource you have. So with this, we could test for semi-quantum instrumentality on certain given assemblages, and in particular, we use this quantum model here, where we have this Bell state here shared by both parties, and consider that Alice measures in this basis here in on her side, and so here is the block sphere representation projected in the XZ plane. And what we have obtained is precisely that the robustness of the assemblage extracted from this is greater than 0. So with this, we have shown that we have answered that question which was left in the diagram of the models negatively. So in a sense, so what this means is that the semi-quantum instrumental model, so this enhancement is increasing in descriptive power by using the the classical communication is not enough to cover all the correlations that you can obtain in quantum mechanics. And also, we can do a little bit more. We can extend this model to admit other visibilities, and this is what we have done. So we consider, instead of only the Bell state, consider the Bell state under some dephasing with variable, with the visibility being a parameter. And what we got is we got this very nice continuous transition between the models, and we see that for a certain low value of the visibility, we get an assemblage that is steerable, but so it's not local hidden, does not admit a local hidden state model, but admits a semi-quantum instrumental decomposition. So in a sense, by just if we consider a projection of the semi-quantum instrumental model to the no signaling manifold, this is not just trivially the local hidden states model itself. It's something more. So we indeed get more power to describe things. So here's what's represented here. This can be organized in a graph. And if we see here, this white region is precisely the first result. So here we have this red curve here representing the robustness of steering for the assemblage, with the visibility here in the x-axis, and with the non-instrumentality robustness here represented in this blue curve. So here we have steering, but semi-quantum instrumentality, and in this region here we have non-instrumentality for a quantum assemblage. And in this dark green region here, we also show that with this model, we can violate the inequality derived by Rafael Chaves and these collaborators in his last publication, Nature Physics. So here we see that even for a quantum model, we have all these correlations. Another way to show this is in this 3D picture here, where if you consider that this ellipsoid here is in a plane, then we have this relationship between all those models. So the quantum states are larger than the ones allowed by the semi-quantum instrumental description. The semi-quantum instrumental description on its side is larger than the local hidden states even for no signaling for the no signaling assemblages. But also we have to consider that they are signaling, so they escape from this plane here, right? Another result that we have obtained is in this very interesting one. So this is, I mean, this is where the physics gets interesting. The way is that we show that the quantum assemblages, they are already the ones with that allows you to get the most of the non-classicality in this model here. So this is represented by this robustness of the quantum model equals to the robustness of the quantum instrumental model. But more than that, if we restricted this side here to be the quantum instrumental model outside of the non-signaling plane, we can substitute this this equality by an inequality by this greater than or equal. So it's more precisely what I'm saying is that for every quantum instrumental assemblage, I can find a quantum assemblage that has at least the same robustness of the quantum instrumental one. So, and we even know which quantum assemblage is this, because if you are given a quantum instrumental assemblage, you know that this comes from a quantum assemblage just by applying that outcome-dependent CP-TP map. And if we take this quantum assemblage here, its robustness is greater than or equal to the one of the quantum instrumental with the map applied. So this result here is very interesting because it says that you using just the no signaling assemblage, you can get the more correlations than you would get by actively using the outcome communication. So it's like so if I state this in another way, I can say that using this actively this classical communication only tends to degrade, only tends to deteriorate the amount of correlation you have on your state. And I only recently have realized that this is, in a way, this is kind of expected, because we are measuring the correlation using robustness, and this map here is a free operation for semi-quantum instrumentality. So this is, in a sense, showing that this is indeed one type of resource monotone for semi-quantum instrumental assemblages. But this is also interesting because we see that this is somewhat more general. If you have an assemblage that comes from quantum models by increasing it with communication, and if we get a robustness type of measurement for this increased model, then using actively the communication will only tend to decrease the amount of resource you have, right? So this speak very briefly. So we actually verified this also with an experiment employing quantum entangled photons in this fully optical setup. Here we just prepared the photons in an entangled state, made tomography on one side. Here we control the visibility with the glass slide, and using coincidence detection, we could reconstruct the assemblages. And with these assemblages employing here, implementing that quantum model that I showed to you, we obtained the experimental data to fill the graph that I showed before. So here is the experimental results. With this, I conclude the talk. So summarizing, we have quantized the instrumental causal model. We have shown that this quantum steering is indeed stronger than previously thought, because we showed that it can remain non-classical, remain quantum, even allowing for classical communication. We have derived this robustness of non-instrumentality, which is a very natural quantifier for this non-instrumentality. And of course, this have many potential applications in a practical scenario, because here we are relaxing this condition of isolation between the parties, but of course we have to ensure the instrumentality, ensure that there is no communication of the value of the instrument to the other variables. But with this, we can prove non-classicality even in time-like separated scenario for the parties. So I open out to the questions, and thank you for your attention.